Hey Jamie.
Hey Adam, what you doing?
Oh, just catching up on a little light reading here. What are you up to?
Oh, just looking for myths to bust.
Nice.
Say, that book gives me an idea. Back in school, our TA told us about a naval battle that was influenced by the Coriolis effect.
Really? That sounds interesting. Let's check it out.
In World War I, a naval battle took place near the Falkland Islands off the east coast of South America about 52 degrees south between the German Navy and the British Navy. The British gunners were surprised to see their salvos falling to the left of the German ships. The engineers who designed the sighting mechanisms were well aware of Coriolis deflection and carefully considered it. However, they neglected the fact that not all sea battles occur in the northern hemisphere. Thus, during the engagement, the initial British shots fell at a distance from the targets much greater than the Coriolis deflection.
Alright Jamie, so we got the myth. How do you propose we go about busting it?
Well, Adam, in a situation like this, there's only one thing that can help us.
And what's that?
A combination of a meticulously crafted diorama and highly informative PowerPoint slides.
On a non-rotating plane, a cannon fired straight at an object will hit it.
But add in the Earth's rotation, and it misses. Why is that?
That is because, while the cannonball flies straight, the object it is being fired at moves away with the Earth's rotation. This is the Coriolis effect.
So according to our myth, the British adjusted their guns to take this into account.
Alright Jamie, well we showed how everything would work in the northern hemisphere. What about the southern?
Well, to answer that, let's bring in our experts from the Ministry of Oceanographic and Atmospheric Affairs.
In the southern hemisphere, body feels Earth rotation in an opposite side direction than northern hemisphere. For this reason, Coriolis parameter is negative. That's implied that in the southern hemisphere, a cannonball veers to the left.
The Coriolis effect is an apparent deflection of an object in motion when it's viewed from a rotating reference frame. So in this image, the circle on the left shows an inertial reference frame where the object in motion, say a cannonball, would look like it's traveling in a straight line. Now, on a rotating frame, the object in motion appears to travel in an arc. So what are these reference frames? When we're standing still and we're watching something rotate, that's a fixed reference frame or an inertial reference frame, like these rims. Now when we're rotating at the same time, that's just a rotating reference frame. This is the same perspective that we have when we're standing on Earth. Because the Earth is a gigantic rotating reference frame, the Coriolis effect can really come into play. Things that are moving on the surface of the Earth can appear to veer to the right in the northern hemisphere and to the left in the southern hemisphere. Okay, here's the math part. In the equation of motion for a rotating frame, the apparent acceleration due to Coriolis is expressed as the product of velocity times the Coriolis parameter, which is defined as 2 times the Earth's rotation times the sine of latitude. If we want to figure out when the Coriolis effect actually matters, we can check out the Rossby number. The Rossby number is just a ratio of advection and the Coriolis effect. It uses the distance of travel, velocity, and the local Coriolis force. When the Rossby number is 1 or less, the Coriolis force changes the course of the object in motion. In our case, it's a cannonball. We can find the Rossby number for the cannonball in the war, or at least one close to it, by filling in those variables I just introduced: length, velocity, and the local Coriolis force. We plug those variables in and we find a Rossby number of 275, way bigger than 1. After crunching some more numbers, we see that the cannonball would only be deflected 43 centimeters, or about 17 inches. Now, if you're aiming for a ship, that's probably not going to matter so much. We can change the length in the Rossby number equation to find out how far the cannonball would have to travel for the Coriolis effect to deflect it significantly. In other words, what would make the Rossby number equal 1 or less than 1? The equation on the top here shows that. The cannonball would have to go pretty far, 4,600 kilometers at 550 meters per second. So 4,600 kilometers, otherwise known as the distance between LA and Connecticut.
Well, Jamie, I think we can say that myth was sufficiently busted.
Yeah, I think we consider that one put to sleep. But you know, this whole Coriolis thing, it reminds me of something about toilets.
That, Jamie, is a myth for another time.